traffic was very bad. I'm moving to an apartment outside of school, so it takes a longer time, especially when the traffic is bad, to come to school. Okay, so so we talk about the interval tree. Oops, shoot. Okay, so and we also talk about the analysis. The analysis is pretty straightforward. It's just because this operation obviously like it takes like at most like the height of the tree, so it's log n. Okay, I mean, but it takes log n to find one interval, and if you want to find all the interval, you after you get that interval, you delete it. The delete takes a log n operation as well, because it's basically a red-black tree. Okay, and then you do the search again. So depending on how many intervals will be found. Okay, say you have k interval, the time it takes is going to be k log n. Okay, so this with the output sensitive algorithm is very, very common. Okay, it's not necessarily the best one in the worst scenario. Okay, it doesn't guarantee the optimum performance when k is large. Okay, for example, you could imagine, okay, in this tree, okay, if every interval has overlap with like the query interval, then k is n, right? So it becomes n log n. Is n log n worse than the optimal one? Think about this. If all the intervals will overlap, I mean, or put it another way, most of the interval will overlap. I mean, the easiest choice would be, you just use any traversal, like in order, post order, pre order. Basically, go through every interval and compare that with the query interval, right? So it's going to take linear time. It's going to take linear time because like the traversal take linear time, and then the comparison take constant time. So it's going to be linear. Okay, you have a number of comparison, to determine like if there's a overlap. But basically like the whole thing takes linear time. So it's going to be better than n log n, right? When k is n. So you can see that, okay, this type of output sensitive bound, okay, output sensitive approach, when k is large, okay, theoretically speaking, it's worse. But when k is small, obviously you have the benefit. Okay, k log n. When k is small, then the k log n obviously is cheaper than linear. Okay, and that's the best algorithm. I mean, this is like out of the scope of this this class. Just want you to understand, like there's such algorithm out there. Okay, and but we haven't talked about the correctness. Usually we talk about correctness first and then talk about analysis. Okay, so let's look at this this operation. First, okay, each node, okay, on the top is stored like You know, the interval tree store the interval at the top of the node, right? And then, you know, at the bottom of the node is store the largest right endpoint, largest right endpoint of its left subtree, okay, of its left subtree. So, yeah, means so this is the first thing I want you to remember, okay, because last time we talked about this, I'm afraid like you might have forgotten. And then this interval search, okay, and by the way, I forgot. I mean, this we are going to. This is a binary search tree. Okay, the order is done by what should I say? Wait a moment. Yeah, I believe it's a right endpoint. So it's a 8, 11, 8, 10. Sorry, let's see. Is it 4, 5? Oh, sorry, left endpoint. It's based on left endpoint. So it's a 4, 5, 7, 15, 17, 22, right? Left endpoint. The order is determined by the left endpoint in this binary search tree, okay? So then, okay, we have the query interval, okay? So I is the query interval, okay? So I and int x don't overlap, okay? I don't know. Where to go? Yeah, we talk about this one. Okay, this one is like yeah, x interval don't overlap. Left x. If there's an overlap, you just report this one, okay? Otherwise, if left x is not nil, okay, so you check like if and the low I is smaller or equal to left x, okay, the left child, okay, the n value of left child, okay. So what is n value? The n value stands for the largest right endpoint in its left subtree. Okay, so if this is large, okay, larger than the left endpoint of the interval, the query interval, okay, it means that, okay, you can, what should I say? Okay, let's use this one. Yeah, I think we have this, okay. So the query interval is 14, 16. 14, 16 don't overlap with 17, 19. Okay, so then we check the 18. Okay, the left child's n value, which is 18. So we know this 18 represent the largest n value of its largest n value of its of the subtree rooted here. So it's 18. So then, okay, you know that, okay, 18 is larger than the left endpoint 14, right? So you know there must be something, okay, some interval, okay, what should I say? this interval must be, if there's overlap, it must appear somewhere here. Because like we are sorting based on the left endpoint of this interval, right? So this 18 must be larger than any left endpoint in this interval, right? Look at here. And at the same time, okay, this 18 must be larger, must be smaller than the left endpoint here. So it's safe to go left because there's no way this interval is going to have overlap with any interval stored here. Okay? So then, okay, let's look at the other case. Okay, so 14, 16, 5, 11, there's no overlap. And then you check, okay, the right endpoint of max value, which is 8. 8 is smaller than the left endpoint in 14, 16. So it means that there's no interval in here. Obviously, like any interval that is stored in this subtree, okay, the right endpoint must be at most 8. So it is impossible for any interval stored in here, okay, to overlap with the query interval. So that's why we take the right-hand side. We go this way, okay, and so on. So there are only these two cases, okay.